So in section 4.4, what we're going to do is we're going to take a look at the motion of bodies under everyday forces. Those forces include, but are not limited to, friction, the normal force, gravitational force. We can later in the centrifugal force. You could incorporate electromagnetic force, right? You can do all of this stuff with Newton's laws. Specifically, though, we're going to look at friction, normal force, and some sort of applied force, like a pull or push.
It's not pudding.
We are. Oh, there it is.
It was a joke. It was a joke.
We are.
It was only 30
We are scared now. We're going to talk about the types of friction.
What a Halloween.
Please listen. We've already discussed in your lab the concept of overcoming friction, being able to move it. And we'll talk about how that's called static. And then once it's moving, you have to then overcome the moving friction, which is called kinetic. But we'll get to that in this section. Okay? So we're going to take a look at all those things. There's a lot in this 3 class periods worth. So we already know this formula, right? We've already seen this a few times. But the weight of an object is called its gravitational force, aka Fg. Okay, the force due to gravity on an object. The force due to gravity. Now, it's really, really, really important that you understand the difference between weight and mass. It's important you understand the difference between weight and mass. Okay? Now, if I am on the Earth and I weigh a certain amount of pounds, and then I go to the moon's gravitational pull is 1/6 of the Earth. So I would weigh 1/6 of what I weigh here.
But your mass is the same.
Okay? But your mass, very good, is the amount of matter that makes up your body. Your mass is unless you lose mass, lose mass, okay, on that planet constantly. But if you go from planet to planet, you can planet hop, your weight literally changes. Did I go over Dragon Ball Z already?
Yes.
Okay.
So you don't
Okay. Yes. So no. So the idea, though, again, is that your mass is fixed. It's not changing. I mean, in this instant in time. So if I could teleport to the moon, my mass would still be whatever it is in kilograms, but my weight would change. Okay? Is that clear? Mass and weight are different.
Does it weight change? Like people say that you wake yourself in the morning or like at night.
Your mass and weight both change then, yeah. Because that's the amount of matter your body makes up. If you eat a sandwich for lunch and you eat dinner, aren't you absorbing that mass? So you're increasing your mass and your weight there. When I say your mass doesn't change, I mean if you take this instant and then a second later you move to another planet somehow, your mass is still the same. If you eat food on a trip to the planet, then your mass changes. But generally, your mass is the amount of matter that makes up your body.
Then why do we say, like, oh, I weigh that many pounds, but it's actually your mass?
So pounds is a force, so it is your weight. But in Europe, they say a certain amount of kilos, and that's your mass that you give. But the amount of pounds is actually a force. It's just the English unit. You know how we use newtons? You know how in this class we use meters instead of feet? So meters and feet is like newtons and pounds. Pounds is the unit, is the English version of the weight of an object. Okay? Pounds. So it's the same thing as newton, just a different unit. All right. If an object weighs 25 kilos, if an object's mass, see what I did? See what I did? I said weighs, and I corrected myself, because you don't weigh 25 kilos. If an object's mass is 25 kilos, what is the magnitude of its weight on Earth? Simple, simple, simple problem. You give the mass, you know gravity, use the formula from the last slide. Okay, we'll do the second part in a moment. Okay, but you're given the mass. We know gravity on Earth. Okay, g is really the acceleration, or negative 9.81 meters per second squared. Now, it says, what is the magnitude? Who remembers from their vectors? Vector is a magnitude and a direction. So if I don't know about the magnitude, do I care about the direction? No. So when I do the math, I don't care about the negative signs, what I'm saying. When somebody says, what's the write this down as a little note. When you're finding the magnitude of a force, it means the actual amount of the force, not whether it's negative or positive. Direction means nothing. Exactly like absolute value. Very good. When you're looking for the magnitude of a force, you can drop all negative or positive signs. It's always positive if you find the magnitude. So what Caroline said is just to do this. She's right. If you want the magnitude of the weight of an object, take the absolute value. Okay? So we want the magnitude of this. So the magnitude of Fg equals the mass times gravity. Since I'm taking the absolute value, I know for a fact that it's going to be positive. I'm looking for magnitude. I'm going to get 245 and a quarter newtons. Okay? 245 and a quarter newtons. Now, that's the weight of the object on Earth. We then want to figure out, and by the way, the other class corrected me, or I corrected myself. I forget what it was. It's not actually 2.64. Something's off by that. Somebody real quick, look up the acceleration. Or no, it was, do this calculator. 24.9 divided by 9.81. 2.5? Verify, yeah? Okay. So this should be 2.5 really. Because it turns out that the magnitude of the acceleration of gravity on Jupiter, I always remembered it as being 22.9, and it's 24.9. Okay, that's what it's published online these days. Now the problem is that Jupiter's gas. It's all gaseous. So there are actually difficulties trying to figure out what the acceleration is on Jupiter. Okay, so you might read online that it's 25.7. You might read that it's 23 point something. The official one that's NASA's is 24.9, they claim. So anyway, I fixed that number in the last class because I was using an old number that I had written down. Anyhow, that's besides the fact. So it says, what about on Jupiter, where the acceleration due to gravity is 2.5 times that of Earth? So on Jupiter, if there's more gravity, you're going to feel heavier. So your answer is not going to be this number, it's going to be bigger than this number. So I could simply take 9.81 and do what? Yeah, I could take 9.81 times by 2.5, that'll give you 24.9. That's the gravity on Jupiter. And then I can take that number, 24.9, and multiply it by 25 to get the weight on Jupiter. So again, if I want to figure out what the weight is on Jupiter, I could do this. I could say the force of gravity on Jupiter is equal to mass times gravity on Earth times 2.5. Because it's 2.5 times larger. Remember, G is 9.81. So 9.81 times 2.5, because it's 2.5 times larger, times the mass. That will give me, what do we get from that? 245, I'm sorry, 2.5 times 9.81 times 25. What does that give me?
Where do you get 2.5?
Look at the problem. It said 2 point, what did it say? I think I wrote 2.64, but it was corrected to 2.5 there.
613.125.
Now, do me a favor. Just take the answer you got before and multiply by 2.5. What's going to happen? Should be the same thing. Why? How come I can just take 2.5 multiplied by the answer instead of putting it down here with all the work? Why can I do that? Because it's the same thing. That's a good answer, but it's not like a reason. What is 245.25? Isn't that mg on Earth? That's mg on Earth. So technically this is 245.25 right here. So you could literally plug in for mg 245.25 and just multiply that answer by 2.5, yielding 613.1.
Because multiplication is,
Associative.
yes.
The grouping does not matter. The parentheses does not matter with multiplication. It is associative. Okay? All right, good. Good. Again, a simple example to start. Let's go to some more complicated stuff though, all right? Talk about, which we have already mentioned, is the normal force. Can somebody explain to us, and you can read it obviously, but explain in your own words what the normal force is. No?
The normal force is the force that pushes you from the back up and keeps you from falling through things.
Exactly. The normal force is a reaction force. So the example they'll give is you drop something or you leave something on the table, it wants to move down, because gravity pulls down. What helps it push up? We call it the normal force. Anybody know why it's called the normal force? The word normal in math means perpendicular to the surface. And the normal force acts perpendicular to the surface. So what do I mean by perpendicular to the surface? Here's the surface, my hand. Okay? It's got to be 90 degrees in every direction. So this is 90 degrees, this is 90 degrees, this is 90 degrees. So imagine a building coming out of the ground. Usually, cross your fingers, hopefully the building is normal to the ground. If it's not, then we have a problem, don't we? We have the Leaning Tower of Pisa over there. Okay, is that what you're thinking of too? Yeah. So traditionally, buildings are made at right angles to the ground, so you could say a building is normal to the surface. So if I have an object, okay, like this now, sitting on an inclined plane, okay, so we have an inclined plane, here's the object itself, the normal force would go off this way in this example. Okay, but it's always perpendicular to the surface. Here's the surface, that is perpendicular to the surface. Okay? If you don't see the right angle, I'll draw it in. Okay, there's the right angle right there. So the normal force is always perpendicular to the surface. Now, in the next example, we're going to talk about how the normal force is not always equal to the weight. Clearly, right now, the weight of Christina's pencil case is 0.1 newtons. So the normal force is 0.1 newtons because it's pushing back up. But if I were to do this, take a look. Still normal force is still 0.1 newtons. The weight is still 0.1 newtons. But if I did this, and I started to lift it and pull upward, eventually what's going to happen if I pull hard enough? Now what's the normal force? There's no normal force. So what's keeping this in equilibrium? Weight's pulling down. My hand kind of pulling up in a sense, right? It's in equilibrium. So as I start to lift, as I start to pull upward, what I'm doing technically is I'm decreasing the normal force. Because I'm helping it out. Think about it. The normal force has to do all this work. The normal force has to push back up to balance the gravity. But if I help the normal force by pulling up on it a little bit, I'm decreasing the normal force until the normal force becomes zero when this off. So we're going to take that idea and carry it into these next few examples. Can I get a reader, please? Can I get a reader, please? Isabel, please, go for it.
If an object is at rest on a table with a mass of 10 kilograms and you are trying to lift it with an upward force of 35 newtons, will it take off of the table? If not, what is the normal force exerted by the table?
Why did I write if not? Because if it comes off the table, is there any normal force? No. So if it doesn't come off the table, we'll figure out the normal force. If it does come off the table, we can technically find out the acceleration. Now, how could this come off the table? If the pole exceeds its... What were you going to answer originally?
Well, I don't know how to word it. If it exceeds like the force of the table, the edge of the force.
What's pulling it down?
Right.
And what's pulling it up?
Oh, you.
We don't know if the normal force is there. It's a question, right?
Yeah.
So who is doing it?
Whoever the person is.
Yeah. So if I pull on this with a force greater than its weight, it will off. So let's figure out what its weight is and see if that's less or more than 35. If the weight is more than 35, it's not going to go anywhere. But if the weight is only 20 newtons and you pull up with 35, you're going to lift it off the table. Okay, if you're working out in the gym, the only way you can lift the dumbbell is by pulling up with the amount of force the dumbbell is or more. If you pull up, if the dumbbell weighs 50 pounds and you try to pull up and all you can lift with is 30 pounds, is it going to go anywhere? No. You don't have enough strength in a sense to lift it off. So that's the idea here. So let's figure out FG first. Let's start givens. This is only in the y direction, this problem. Keep that in mind, by the way. We're going to see examples in the later part of the section where in both x and y. So let's figure out what the weight of the object is using mg. P is like pull, or you could use A for applied force. Either one is fine. It's some external force, okay, caused by a person, a machine, a cable, whatever it is. So obviously this is an easy. Don't use a calculator. Please don't use a calculator. Multiply by 10, just one yes, one spot. 98.1. So it's way too heavy, right? It's way heavier than the amount of force that I'm trying to lift it with. So what's going to happen as a result? Is it going to lift off or no? No. So it's definitely still on the table. The question now becomes, let's figure out what the normal force is. Okay, let's figure out what the normal force is. So to do that, we look at our free body diagram, which I was nice enough to draw. In the future, I'm not going to draw those. Those are ones that you're going to have to, understand how to draw. The weight is coming from the center. The pole is applied at the top. The normal force is perpendicular to the surface. Which of the arrows, by the way, here's how you're going to do all of these problems for this whole chapter. Which way are the arrows pointing? That's question one. Which arrows are pointing up? or positive? Because we're only up and down now, but if we were left or right, it'd be left or right. What's your positive?
North.
Okay, which ones?
These ones and this.
Yeah, which variables are
FP
good and
and FN.
good? And pulling down, everybody is? Yeah, gravity as always. So start by doing that. Literally list your forces. If they're pulling up, you put positives. If they're pulling down, you put negative. If it's to the right, it would be positive. If it was to the left, it would be negative. But that would be in the x direction. This is only in the y direction. Now, what did Newton's second law tell us?
Object in
Every action has an equal.
That's another one of them. You both just named them both. What's the other one?
It's like for every push, there's an opposite.
Yeah. What do you got? That's it.
Every action has an equal.
Not that one. I think you were saying something else. I'm sorry. It's all right.
Object of rest.
Oh.
something with math.
It's his most famous law. It's an equation. Okay. That's all it is. I think it was MA. So, Newton's laws told us that the net force on an object equals mass times acceleration. The net force on an object equals mass times acceleration. Now, the question I pose to you, is this object moving?
No.
So does it have any acceleration?
No.
So we can do what over here? Goes to 0. Okay? That's how you're going to approach every one of these problems. F net equals MA in a specific direction, in this case the y directional. F net literally means list all the forces. F net, this is where you might want to write down notes if you're confused ever. F net is the equivalent of just listing all the forces. Okay, all the forces are listed. You then could put the mass of 10, but it's times an acceleration of 0 because it's not moving. So in this problem, we put a 0. If it were moving, we can determine the acceleration. That's what we would be able to figure out based on the forces acting on the object. At this point, all I need to do actually is solve for, what are we looking for in this problem? Normal force. How do I move FG over? Add FG, and then, how do I get rid of FP? And take a look. That makes a lot of sense. I want to make physical sense of our mathematical answer. If I were not pulling on this object, if I were not lifting it or trying to lift it, the normal force would simply be equal to the gravity force, or the weight. Right? Currently, look around you. Every object that's at rest right now on a surface, its normal force is equal to the weight of the object. It always is. But as soon as I start lifting on the object, I'm helping the normal force, aren't I? So the normal force doesn't have to do as much work. So the normal force will not be equal to the weight anymore. It will be something less than the weight. So take the weight, subtract however much you're pulling to see what's left for the normal force. Okay, use a little bit of conceptual stuff, not just mathematical. So again, the weight of this calculator is a half a Newton. The normal force is a half a Newton. But as soon as I start to help it and pull up a little bit, now the normal force is something less than a half a Newton. I can take the half a Newton, subtract the maybe fifth of the Newton that I'm pulling with, and I'm left with some amount for the normal force. Same thing here. However much I'm pulling up by gets deducted from the weight to see what's left for the normal force. Okay? So, think again, logically, please make sense of the answer. The object's weight is 98.1. The normal force is definitely less than that because you're helping pull up on the object. Okay? Hey, do your best this weekend. I recommend maybe problem sets 4-1, 4-2, 4-3. Okay, work on that lab, get all that stuff done. So, a small object is stacked on top of a larger object, and they are both on a table. If the masses are 5 and 15, obviously the small one is 5, the large is 15. We're assuming constant density. What is the normal force acting on each of the two objects? On each of them, so not individually. Not together. So what do we do for a problem like this? What's the first step you might choose to begin with? Draw a diagram, okay? And we can specifically draw free body diagrams of these as well. So an overall diagram is very simple. I'm going to sketch that real quick. There's the overall diagram, done. Okay, free body diagram needs to be this. Yes. I'm going to use bigger and smaller. Okay? And this is one of the times I'm not going to use a dot. I'm going to use a square to signify the larger and smaller of the two. So the larger, well actually let's start with the smaller. The smaller one's easy. What's acting on the smaller mass? What's pulling it down to the girth? Always. Gravity. We'll call that FG1 for object number 1. Now, what is supplying some sort of a response to gravity so it does not fall through that? Fn, the normal force. And I'm going to call that Fn1 for object number 1. The normal force acting on object number 1. Good. Object number 1 is the easier of the two. Object number 2. What is always pulling it down? Again, as always, everybody? Gravity.
Wait, what do we put something on top of it? Gravity plus.
So we have gravity pulling it down every time, as we know. Okay, what pushes back up always? Normal force. Shabana's ants in her pants, so she's going to tell us now the next part. She was jumping to say it. What else is acting?
Gravity of the first object.
Yeah, the weight of the first object is pushing down on it. Keep that in mind. What is being applied on this object? If you stack two objects, the bottom one is feeling the weight of the top one. You know that. You've done chicken fights in the pool. You know, you put somebody up in your shoulders. Right, chicken fights?
Yeah.
Put somebody up in your shoulders and you feel their weight. It's because they're stacked on top of you. So object 2 feels this. Ready? A push down on it. So draw an arrow down on the top of it. And what is the value of that? Well, it's the weight of the upper object. So that's FG1. Bless you. So the weight of the upper object, or the weight of object 1 is acting on object 2. So we have FG1 pointing down. Take a look. Look at the bigger object. Both FG1 and FG2 are both acting down, which means that it's really feeling a lot more weight than it should because another object is stacked on top. Okay, it doesn't matter where they are in the diagram. All that matters is that they're down. If they're down, the sign becomes negative in the mathematical portion. So we're going to approach that the same way now. So we're going to do what we've been doing for object 1 and object 2. Luckily, we're still only at the y direction. We don't have to worry about the x direction at all. That's the lucky part right now. Okay? So let's go ahead and take a look at this. So we've got, for object number 1, the sum of the forces in the y direction equals ma. Okay, again, if you're not sure what I'm writing here, this symbol is a sigma symbol. It means the sum of the forces. It's the same thing, and I'm trying to show you different notation so you're used to it. It's the same thing as writing this, F net in the y direction. Remember, F net means all the forces together. This little e symbol means sum of. The sum of. The actual symbol, if I write it properly, looks like this. Okay, it's a sigma symbol. For those that are interested or know about fraternities or sororities and letters, sigma. So the sum of the forces in the y direction equals ma for the acceleration in the y direction.
What's that squiggly line? Oh, is that what you just said? Oh my god.
So the squiggly line means the sum of. The sum of. It's the, you could do that or you could write F net, Nick. Either one. It's all right. Now, the sum of literally means sum them together. FG1 and FG2, I'm sorry, object 1. On object 1, we only have FG1 pulling down. So we look at object 1, and we see in the y direction, FG1 is pulling down. So it's negative FG1. Which way is FN1 pushing? Up. So we put positive FN1. Now, is the object moving?
No.
So there can't be acceleration. It's in a state of
Equilibrium.
equilibrium. or rest, that works. So therefore, MAY is simply,
Zero.
yeah, negligible. Okay? That's funny. So, and I do know that, because I was born a long time ago. Not a long time ago, but that's from a while ago. So this goes to zero because acceleration is zero, so the whole right-hand side becomes zero. So it turns out that the normal force provided to object 1 is really just equal to its weight, which makes sense, because it's on top. Think about it, right? You take, I need a flat object. You take a few objects. Sorry, I just don't want something on an incline or else it doesn't truly, yeah, give me one of your books. So you take this object, right? It has a certain weight pushing down, the table pushes back up with the normal force. It's equal and opposite, it's in equilibrium. I take this object and I stack it on top now. Now the normal force from the table is the sum of this and this. We're going to see that in the second object. But the first object, meaning this little planet itself, has a certain mass, and the normal force coming back up from the laptop is Fn1. And Fn1, and then the weight of the object, the mass times gravity, the weight of the object are going to be in a state of equilibrium, they're balanced. So it turns out that Fn1, the normal force acting on the first object, is just equal to the weight of the first object. How do I do that? I add Fg over to the right-hand side. It's got a negative sign. I remember to add it. Now remember, the little g and the n, these are subscripts. These are not variables. Why is that funny? They are not variables, they're subscripts. What is the formula for Fg? How do you find the weight of an object? What could you replace that with? Ariel? Yeah, m times g, and this is the mass of object 1. So I'm literally replacing this right here with the formula, okay? F sub g equals mass times gravity. F sub g equals mass times gravity. So now we have mass of object 1 times gravity. So take the mass, which is 5 kilograms, multiply it by 9.81, 4905.
I thought 9.81 before, because we're in Y, so
What is the?
falling, it's not actually falling over the.
It's not falling. There's no acceleration involved. But to calculate weight of an object, it's a force due to gravity. Remember, the weight of an object is always mass times gravity. Siobhan, if it were in a state of free fall, this would be true, and the acceleration at the top, AY, would have been negative 9.81 also. And that's a feeling of weightlessness. If you fall in a vacuum, you wouldn't actually know you were falling. It's kind of crazy. You would have no idea you were falling.
Then what is the gravity isn't 9.81, what is that?
What?
What do we do what gravity is not 9.81?
No, it's you're on a different planet. Different planets.
Always 9.81.
On Earth, yeah.
Always.
So if we're calculating FG1 would just be 5 times negative 9.81?
Yeah, but remember that we're solving for the normal force. We already took into account the negative sign. Where did we take into account? Right here. See this negative sign here? You see that? Because that showed us that the direction of the vector was down. Normal force was directed up. So we don't use the negative for this anymore. That's what I was saying. Like I think like
If we're calculating FG,
you don't use negative. That's what I'm saying. So it goes negative in the formula, but then when you move it over, what does it become in the end? It becomes positive. So Nick, yes, we're accounting for the negative 9.81, but using our vectors, not, remember, whenever we use G now in this chapter, we're going to use 9.81. The negative only comes from the direction from the free body diagram. Units? Who's that scientist? What's his name? Newton.
Oh, that side.
Oh, that one. Come on, units of force, Newtons. Right away, Newtons. Okay?
I love using the Einstein to calculate.
They celebrated recently the 100th anniversary of Einstein's theory of relativity. Pretty cool. I got to read about it this weekend. It was actually really interesting. Somebody sent me an article about it. It was really cool. The concept was how Einstein came up with the theory of relativity and how the idea of that people can't really get the speed of light, but as you approach the speed of light, things start to warp around, things change, time dilates, and it's really the anniversary of when he celebrated that or came up with that idea. the normal force, again, on the first object. Now we have to find the normal force on the second object. What is it going to be, bigger or less than that number? Why bigger? The object itself is bigger. And what else?
Yeah, the mass.
And what else?
The mass of the object.
The mass of what object?
Two. Object two.
Okay.
It has the mass of itself and the one on top of it.
Yeah, its own mass plus the mass on top of it. That's the key. There's two objects now pushing on the table. Think about it. Fn1. Fn1 is the normal force provided where? Right here. Look where it is in your diagram. Where is this coming from? It's coming from the top of object 2, isn't it? Think about it. The top of object 2 is like a table for object 1. So the top of object 2 pushes up with this force. Why does it do that? Because this pushes down on object 2. So object 2, when we find Fn2 here, it's going to be the table pushing back up. Well, the table is pushing up on this and this, both really. Okay, the table has to support both objects. So now we have to do the same thing we just did, but use this free body diagram. So we're going to have a negative Fg1, negative Fg2, positive Fn2 equals Ma. It's the same exact approach as we just had right here. Okay, I'm literally going to do the same thing, but for object 2 now. So I have the upper object pushing down on it. The lower object pulling down. Whoops, I'm already putting in my formula. We've got the normal force pulling or pushing back up from the table. And that equals 0 because it's in a state of equilibrium. Again, let's take a look. Fg1, that's the weight of the upper object. Fg2, that's the weight of the lower object. Those things are both pushing down. So both objects' weights are pulling down, so therefore they're both negative. The normal force from the table is pushing back up, so its value is positive. Where am I getting this equation? I'm literally just looking, I'm literally just looking at my original free body diagram in the top left. Look at the top left. This is negative Fg1 minus Fg2 plus Fn2. That's this equation right here. Negative Fg1 plus minus Fg2 plus Fn2 equals 0. Why is it 0 again? Because of equilibrium. And now what you're going to recognize is that Fn2 is simply the addition or the sum of Fg1 and Fg2. How do I know that? Well, I just take this is negative, add them over here to the right side. So the table pushes back up with a normal force equal to the sum of both objects. Whereas the other normal force only had the weight of one object. Okay, because that was only supporting the little object. This was the normal force supporting the little object. This is the normal force supporting both objects from the table. How do I do that? So I simply go like this. M1g plus M2g. You could technically factor out a g and sum together M1 and M2 and multiply it by g after, or you could just do your math the normal way you'd plug in at this point. Okay, so Fn2, the force from the table, is going to be the mass of the first object, which was 5, times 9.81, plus the mass of the second object, which was 15, times 9.81. So we're simply adding together the weights of both objects. So I've got 49.05, which was the first mass. That's this right here. Or the first weight, I should say weight. Plus the weight of the second object. What is that going to give us? What do we get from 15 times 9.81? Mr. Gray? 147.15. Yes. Awesome. Summing those together, giving us 196.2. So if you want to write a little note to yourself, you should write down the fact that the second normal force is bigger than the first one, because the second normal force is exerted by the table. Okay, the normal force of the table, it supports both objects. That first normal force we calculated was the supporting force on the first object only.
The second
Supports both objects' weight. Or weights, whichever. Okay, example 4, a force of 100 newtons is applied to a box that's at rest on a table in the upward direction. So what am I doing? I'm trying to lift the object up. You know right away what that means. It's exerted upward, trying to lift it up. If the mass of the box is 8 kilos, will the box move off the table vertically? We had one of these questions earlier, remember? Will it move, will it not? It didn't earlier. What do you think's going to happen now?
it will.
Probably will move now, we'll see. If so, if it does move, with what acceleration? If not, what is the normal force provided by the table? So remember this, we looked at, I think what's it called? That's a case. And the question was, can I pull up with enough force? I can't, so it's not lifting. If I did exert more than enough to cover the weight, it's now moving, right? And if it's moving, it has acceleration. So if it moves, find out the acceleration. If it doesn't move, what's the normal force? It's one question to the other here.
When you're like lifting that up, do you overcome the force and when it lifts off the table or when you start moving? Because like when you lift
I know,
like,
yeah. Assume it's standing tall. Assume it's standing tall, there's like a rope on the top. As soon as you exert the amount of force that's equal to the weight, it will lift off. It's like a brake point. It's like as soon as you get above.
because like when it's here.
Yes. You're not technically lifting the full weight because it's at an angle, so you're lifting the weight times the sine of theta. So you're only lifting a component of its weight when it's at an angle. Okay, that's why, how many people have ever done push-ups before? Okay, we all know that the cheap way to do push-ups is to do this, right? And to go at an angle like that. It really doesn't take much at all to do a push-up that way. Because your weight is not really doing what's supported. You're supporting a fraction of your weight by doing that. That's why you do push-ups. If you want to do tougher push-ups, instead of doing up, you put your feet up here, put your head down there. And now you're almost doing your full body weight. If you can get your body vertical and do like a handstand, and while you're doing a handstand, do push-ups.
What if you're hanging?
Today, no. I worked out hard yesterday. Another day, I probably could do those. I do a lot of yoga, so I've been able. It's a balance thing. It's not about strength. It's about balance, really, though.
What if you're hanging from the ceiling?
What?
Let's keep going. So, from the ceiling?
That's like pull-ups.
Yeah.
No, but
then-
your feet would also have to be on the ceiling.
Well, then you'd be doing like sit-ups. That's the Gopi example I came
No,
up
but you would
with.
be like that. Like,
Those are back rows actually. Believe me. That's a really good workout too. All right, a force. So we already read the problem actually. What am I doing? So we're pulling up on this. Will it move is the question. So what is the weight of this object? What is the weight of this object?
8 kilograms.
No.
That's the mass.
Thank you. And that's the first thing we need to know. The mass is 8 kilos, not the weight. So let's start by listing that. Now, if FP is more than the weight, it lifts off. Again, you need to write this down, write it down, if that thing clicks you right away. If the force pulling up is more than the weight, it's going to lift off, it's going to move. Okay, it's got to come off the table if it's more than the weight. So the first thing you really need to do is figure out what is the weight, and then we'll discuss whether or not it moves. So what does the weight turn out to be? Well, Fg is equal to mg, which is 8 times 9.81. What does that give us? Nick, what's your question?
how is this different from 4-3?
4.3. 4.3. Oh, 4.3, we learned Newton's second law, which was F equals ma. Now we're just applying it. Because these are the easy problems, they're all one-dimensional right now. Once we get to two-dimensional, it gets a little bit tougher.
Oh, great.
It's not going to be all easy problems. What does the weight turn out to be?
78.48.
78.4. 4? 8. 4.8? Got it. So this is the weight of the object. How much force is being applied upward?
Wait, mass is that
Okay?
What is it?
Mass times gravity.
And that equals the weight.
So the force upward exceeds the weight downward. 100 up, 78 down. Use common sense. Up is bigger than down, means it will lift off. That's how you can start this problem. So therefore, we are finding the acceleration. Again, it says, ready? First question. Will the box move off the table vertically upward? The answer to that is yes. So if so, with what acceleration?
So our question now is find the acceleration. The next part says if not. So we don't need the next part. We don't need to do it. Cross it off because you don't need to do it. Why can't there be a normal force? Because it's not what?
It's not stable.
Yeah, it's not at rest on the table in equilibrium or in some sort of state where it's not moving. If I lift this calculator off the table can't be a normal force anymore because it's not in contact. Normal force needs contact. Okay? It's one of your contact forces. So the question is, what is the acceleration? God bless you. So this is one of those times where we can use that formula we've been looking at. Sum of the forces in the y equals MAY. And we're not going to set this equal to 0 now. We're not going to cross off MAY and make it 0 because it is moving now. Our goal is to figure out what is AY. What is the acceleration? So let's list all the forces first. What's acting down?
Gravity.
What's acting up?
100 Newton.
Yeah, 100 newtons or FP. Either one is fine. Equals MAY. Our goal is to find AY. I could easily solve algebraically. I'll plug in mg for FG. That's the formula for FG. Remember, FG equals mg. Always, 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 always. FP is given. Just carry it down. Let's divide by mass to get A by itself. Does everybody see how that gets A by itself? Does that make sense what I just did? I replace FG with mg and I divide it by m. This is your answer right here. You have this number. mg was given, or you wrote it down, it was 78.48 or something like that. And then FP was 100. The mass of the object was 8. Plug that in, you get acceleration. The acceleration needs to be positive because it's moving up. You're lifting it off the table.
Do you have to put y since there's no x force?
In this problem, no, Nick, you absolutely don't. Everything is vertical in this problem. So you could have just done sum of the forces equals MA. You don't need the y subscript everywhere on the forces and then MAY. You can just use MA, it's fine. But when we get to two directions, you're going to need to use MAY and MAX separately.
Why is replaced for FG and not replaced for
So this is the weight of an object, Fg. And to calculate the weight of an object, you take its mass times the gravitational constant. This was given as 100. So we're not going to have to put anything in for it because this is Fp, the pull, upward. Okay? And we should get a value of, what do we got?
2.6.
2.69, indeed.
Did you just
2.69.
78.48?
Yeah, of course. Because you already calculated, feel free to plug them in. My units of acceleration are always what? Meters per?
Second squared.
There it is. Don't forget that square. Okay? So, we've done a few problems so far now. The concepts have been similar. Sum of the forces equals MA. Remember I told you that day? This is going to be your governing formula for all these problems. That's what makes these problems pretty easy. You're going to have some sub-formulas, like for example, what Christina asked about. Fg equals mg. We need to replace Fg with mg. We're going to see later in this section, maybe today, maybe in the lab, with the force of friction. And friction has its own little formula you're going to plug in for friction. But in general, the formula you will always use is F equals ma. The sum of the forces, really, equals ma. Okay, in the vertical itself and in the horizontal by itself. All right, one more that might help you a little bit with your extra credit problem. A person rides an elevator while standing on a spring scale, analog, the one I told you to use. What does the scale read if the person's mass is 10 kilograms and the elevator is accelerating upward? What would the acceleration of the elevator have to be for the person to feel weightless? Okay? Now, think, please, for a second. When it accelerates upward is when it starts moving up. Remember the beginning? You hit the floor, you want to go, the door's shut. You feel a little push on your legs in the beginning, right? When it moves up. If it moves up pretty quick, you'll feel a little push, like it's actually harder for you to stand. Then if the elevator stops, gets to the top, and then just as it's starting to move down, you kind of feel a little bit lightweight for a little bit. So our answer, since it's moving up with acceleration, should be more than our actual weight. Does the theory make sense? You should feel heavier than you are when it's moving up accelerating. When it's accelerating down, you'll feel lighter than you are. You could write that note down if you want for conceptual stuff, right? If it's accelerating up, you feel heavier. If it's accelerating down, you feel lighter. Okay, you feel lighter when it's accelerating down.
So wouldn't it just be to reverse gravity?
The second part?
Oh wait, yeah, to feel weightless.
Yeah, absolutely. Very good. And we'll come to that conclusion after we do the math, but that's a really good jump there. So we've got the mass of the object, obviously, is 10 kilograms. We've got the acceleration is 3 meters per second squared, and that's upward. It's only in the y direction, so I'll do what Nick asked last time. I won't use AY, I'll just use A because it's all vertical. I know that the sum of the forces in the y direction, or in the, see, I just did it, see, have it. The sum of the
formula sheet?
What's that?
The sum of the x equals.
This is on the formula sheet, just like that, right there.
Yeah, I know that.
Yep.
I know that.
You have a formula sheet, just look at it, right?
Yes.
Thank you. So sum of the forces equals MA. Now, what force is pushing up? What force is pushing up on the person from the scale? Okay, the elevator itself is moving it up, but what's the force? Remember, we need to identify a free body diagram on the person. Here's the person. What's pushing up on the person? Normal force. What's pulling down on the person? Keep working, keep working. Okay, normal force is up. Gravity is down. Does that make sense so far?
Yes.
Now, before I give you a minute break, the normal force is what the scale reads. Normal force is literally, and you can write that note down also. Normal force is what a scale would read. So the scale is going to fluctuate on the elevator because you're accelerating. So really all we need to do here is solve for normal force. When you solve for normal force, you get MA plus F sub G. I'm just going to add FG to both sides. So I'm going to move this over. What a scale reads to you is literally the normal force. That's why, have you ever stood on a scale before and pulled down on a table? Try it sometime. Stand on a scale, pull down on something. The weight will shoot up. Because when you're pulling down, it's like you're now holding the table. If you're holding the table, the scale's holding the table, so the scale jumps up. If you stand next to a table and take your weight and push off the table, now the scale is not supporting all your weight because a lot of your weight is being supported by the table. So the scale drops down because when you push up, there's less normal force to the ground now because the table's taking some of the normal force, the ground is some of the normal force, so the scale will go down. That's an example using a scale by pulling and pushing. The elevator one is a little bit different because there's acceleration involved. But the idea here is that all we needed to get was normal force because the normal force is exactly what the scale will read. Okay, take a break real quick.
Is this the same thing as like those planes that?
Take a break. Move your legs around. I know you have over here, Goose.
The planes that like go straight down and you can see them.
That's what we're going to see in a minute. That's what we're going to look at, okay? Yeah, get water, walk around the room, just stretch your legs, that's all. Control yourselves, control yourselves. We know the weight of an object is equal to mg. I'm not even going to comment. The weight of the object is mg. Guys, come on. I won't give a break next time. I'm trying to get you a little energy because next period's a lab and you got to focus on this. So we have the mass. Gravity is 9.81. We have the mass. Acceleration is 3. Literally plug in. Okay, literally just plug right in. Use your actual calculator, Gabe. Sorry, the mass is not 3. What was the mass? See, you distracted me. What was the mass? 10.
And this is for the test. Extra credit for the test.
What do you get? What do you get? What do you get? Yep. Very good, Sam. 128.1. Now, here's something you want to write down as a note to recognize this. The actual weight of the object is 98.1. That's over here. Take a look on the right. mg is the weight, isn't it? Actual weight is 98.1. But the scale is going to read 128.1 if it were in newtons, obviously. Okay? Because it's accelerating upward. So the scale is feeling that acceleration or incorporating it into the problem. And as a result, you feel like you're heavier. Seriously, try it. If you don't even do the extra credit, next time you're in the elevator, if you go to a higher floor, as soon as the elevator starts to move, is the fluctuation you have to look for. Again, as soon as it starts to move, that's the weight you feel. So 128.1 would be the weight you feel as it lifts off. Now, I'm going to help with the extra credit. As the elevator eventually starts to move at a constant rate, you'll go back to what? 98.1, because that's your actual weight. Then the elevator will start to slow down, and it'll decelerate to slow down. It'll slow it down the other way. So instead of being 128.1, instead of being 98.1, it'll go down to probably like 58.1. You'll feel less weight when the elevator slows down on the way up. So literally feel this and try to look. So here's what you're doing for the extra credit again. You're videotaping. The other person hits go on the elevator or for 10 or 8 or whatever. As the elevator lifts off, you need to make sure it's being recorded. You're going to see it spike. So it's going to show your weight. Say your weight is 140. It's going to show it, right? As soon as the elevator starts to move, it might jump to like 150. Then it's going to reach a little bit of a steady rate. Once it stops accelerating, it's going to move at a constant velocity. It'll drop back to 140. Then at the end, you're going to see it's going to slow down at the top, the elevator. You're going to see the weight drop down to like 130. Okay? It has to do with the feeling of weightlessness and added weight. So your goal is to videotape from start to finish the elevator going up and the elevator going down. You're going to see a spike, back to your weight, and then a decrease on the way up. And then on the way down, you're going to see a decrease, back to your weight, and then when it slows down at the end, you're going to see a spike again. Okay, it's going to be symmetric in 2 different ways. Okay, so try to do this, okay? Try your best, and I want you to try to explain it in the video as well. This is the prime example to use to explain. See this MA? If A is positive, you feel like you're heavier. That's if acceleration is up. But if you start moving down from the 10th floor, say you're at rest, and you start moving down, that acceleration will be negative. So this would be a negative, making your weight feel less than it actually does. So the question after this was posed, and Caroline's going to answer it for us, was what would the acceleration have to be for the person to feel weightless? So to feel weightless, Caroline, what should it happen here?
It has to be the same or more than gravity.
Yeah. So this, to be exactly weightless, should be negative 9.81. So if you were in a free fall, that's why I said you feel weightless in a vacuum, this is it. If the elevator could accelerate at negative 9.81, you would end up with negative 98.1 plus positive 98.1, and what would the scale read? 0. You would feel literally weightless. So if somehow that elevator could accelerate downward with negative 9.81 meters per second squared as its acceleration, you would feel weightless.
It would have to be exactly 9.81 to feel weightless, but not lift off the floor. Like if it accelerated too fast, you would like something to the top.
This is going down,
Yeah.
only down.
Yeah. So if you were in an elevator and like I'm literally thinking like a James Bond movie.
Oh, yeah, I see what you're saying. So if the elevator started falling
Yeah.
and you weren't falling with it kind of thing,
Yeah.
the molecules in the elevator, you're kind of contained in. So you probably wouldn't, well, if it fell fast enough, yeah, you would hit the ceiling. Absolutely. It'd have to be really fast. Probably a lot faster acceleration than that.
Yeah.
For you to literally go smack, like hit the ceiling like that? Yeah.
Well,
I mean, it's happened on airplanes. Why do you think when there's turbulence, they tell you to buckle up? Has anybody ever been in a crazy turbulence where stuff has moved?
Yes.
Have you
No,
ever?
that's like my nightmare.
It's one of my nightmares
I
too.
hate planes and I've only been
I don't want to be there. You see, like guys, cups and plates of food.
Yeah.
If this happens, will literally smack the ceiling. It's like nuts. It's scary to think about. It's not awesome. So to talk about the lab, let's first talk about friction. So we need to discuss what friction force is. It's a force that really opposes the motion of an object traditionally. Okay, it opposes some applied force. Now, rolling friction is different. We're going to specifically in this class look at sliding friction, assuming there's no wheels. Wheels act very differently. Okay, so we're generally talking about sliding friction, the contact between two surfaces. Now, if we think about this for a second, imagine if I want to move this garbage can and I want to slide it across the room. It's pretty easy to do that, right?
Yes.
But what if I sat on top of it and asked you to come move it? You gonna be able to move it? Probably not that easily, right? Why is that? Yeah, I'm adding a lot of weight down, right? I'm pushing down on it. Well, as I push down on it, to slide left to right, there's a lot more friction. Look at this, I'm pushing a lot. Whereas doing this, it moves easily. So, as I apply more downward force, friction suddenly goes up. And when I apply more downward force, isn't that really going to mean that the normal force is higher? Think about it. If the object is heavier, more normal force is needed to counteract it. So if I sit on top of here, what I've really done is I've increased the weight of the object, but I've also increased the normal force. That's what I've done by sitting here. And by increasing the normal force, it turns out that I'm increasing friction. So it turns out, and we're going to see this in a moment, that friction is proportional to the normal force. That symbol means proportional to. As one goes up, the other goes up. They are directly related. Again, friction is directly related to the normal force. It's actually in the formula we're going to see in a moment. Okay, it is related to the normal force. They are directly related. They are directly related. We'll talk about two types of friction, static and kinetic. Static friction. Here's static friction. Ready? So I've got this roll of paper towels. It's sitting still. I want to get it moving. I push. It's not moving. It's not moving. It's not moving. I finally get it to move. And once I get it to move, it's actually pretty easy to move. Right? Ever do that before? Once you get something going, it's pretty easy to keep it sliding. Furniture, try to move a table or a couch. Once you get it moving, it's pretty easy to keep it sliding. Part of it's inertia. Part of it's the idea of wanting to stay there. Yes, to stay at rest. But the concept of static friction is what explains it really. Static friction, it opposes relative motion of two surfaces that are stationary. And when that happens, this electrostatic force between the molecules develops. On the molecular level, there's a little bit of an electrostatic force keeping these objects together. Once it starts moving though, there's no longer an electrostatic force because it's not static, it's not stationary. So when it's moving, you don't have to compete against that tiny, tiny electrostatic force that's there when it's stationary. So if I want to move my iPad, it's hard to move it, but once I get it moving, it's pretty easy to move it back and forth. Okay, yeah?
So after an hour, it becomes static friction.
Yeah, so what you'll see is this, ready? And I'll draw a graph. You're going to see this today in your lab. If this is force, and this is time, what you'll notice is that you apply force, you apply more force, you apply more force, and then what will happen is it'll start moving and it should do this. Okay, but you'll see that spike in the beginning?
Yes.
That spike in the beginning is the amount of force needed to overcome static friction. But once you overcome static friction, then you have to overcome kinetic friction. Let me try to move this up. Hold on.
Like sometimes for the project it'll be hard because for some things you'll have to roll it down the ramp, but you'll have to overcome that friction.
Yeah, but then once it gets going, what happens?
Then it goes down.
Yeah, it goes too fast. That's going to be part of your project. That's a great part of your project. A lot of you have noticed that already. Okay?
It's like the opposite.
You know, don't give too much away. So once you get it going, though, it's easy to keep it going. That's Fk. So Fk is lower, the force of kinetic friction, we're going to see in a moment. So static friction takes a lot. Now notice, until it's moving, what kind of friction do you have? Once it starts moving, yes, you have kinetic. But before that, you have static, even when it's not moving. So ready, watch. And this is where it's interesting to watch and understand. I push with a half a pound of force. Is it moving?
No.
I push with 3/4 of a pound. Is it moving? As soon as I get to 1 pound, though, it starts to move. So static friction takes on a range of values depending on how much you push. If I push with 0.25, it pushes back 0.25. If I push 0.5, it pushes back 0.5. Until I overcome static friction's maximum amount of, let's say, 1.0 or whatever it is. So static friction can take on a range of values from 0 up until its max. So for static friction, we usually say that it ranges from 0 to its maximum possible value. Again, If I push an object with 2 newtons, it can't push back with more than 2 newtons. It's not possible. So it only pushes back with 2 newtons. But then I push with 3 newtons. Now it pushes back with 3 newtons. Then I push with 4 and 5 and 6 and 7 until I overcome static friction, and then it moves at 7. So that's the maximum static friction force allowed. Okay, the maximum. You probably saw a little bit of this in that lab you turned in today, when you had to just get the refrigerator moving, and you noticed that you saw the friction value that caused it. That was your maximum. That's what I was pointing toward. Okay. Kinetic friction is objects that are what? If it's kinetic instead of static, they are not stationary, they are moving. So there's 2 contact surfaces that are sliding across one another. Okay? Rub your hands together, right? In the winter when it's cold, you create heat because of kinetic friction. Kinetic friction. Okay. And the last slide for us today, but this is what you probably will need for your lab, and we'll talk about this. Friction is represented by the formula mu. This is called mu. Pronounce mu. Okay? It is the static or kinetic coefficient. The higher the mu, write this down, the higher the mu, the rougher the surfaces, or the more friction. And think about it, they're directly related. If you change mu and make it bigger, FF comes out to be bigger, because it's a multiplier. So take an FN, take any number for FN, make FN 10. If you change mu, you change FF. They are directly related. As mu goes up, FF goes up. The more mu, the more friction, the rougher the surfaces you have. Directly related. This is what we're going to exhibit in today's lab. Now, in today's lab, my goal is to get the data collection process completed. Okay? To do that, we're going to have to do this in a expedited fashion. Okay? Yesterday we ended class by specifically talking about this concept of mu. Okay? And in that quick lab we worked on yesterday, where you had to pull on the object and determine the amount of force that it was being pulled with, that lab is really teaching us how to find mu. I'm going to go into that lab also today. So I want to do a little bit with friction, then go into the part of the lab that we haven't gotten to just yet.
What if we didn't finish it?
You didn't finish the data?
Yeah.
You have to do it today. A lot of groups that didn't finish, I think every group, maybe your group didn't finish?
We didn't finish one part.
So you have to come after school today and finish it. The stuff's still out over there. So finish it at some point in time when you have free time. Okay? All right, now look at a problem so we can see physically what's happening here. Okay, so we've got a 24 kilogram cart that's at rest on a horizontal floor. And it requires 75 newtons of force to get it going, to get it moving. What is the coefficient of static friction between the crate and the floor? Now, there are 2 types of friction we talked about already. Static and kinetic. Static is the amount of friction, or the type of friction that you're overcoming just to get something moving. Once it's moving already, now you're pushing against kinetic friction. So in your experiment, in your project over here, you're technically overcoming kinetic friction while it's in motion, while it's sliding down the ramp. But a lot of you have noticed this. A lot of your groups have been doing a great job and picked up on the fact that sometimes it's very difficult to overcome static friction just to get it moving. And then once it's moving, it slides way too fast. So there's that balance between static and kinetic friction. So this problem specifically says it takes 75 newtons to set it in motion. That means to get it going, not to keep it going. Okay, to get it going. So by default, you know already that you're looking at static friction. I also happen to be nice and wrote, find the coefficient of static friction. Okay, so right now, we've got this object, right? It's sitting here. You apply a force on the object, Fp. We'll call it M1 or mass 1. Object 1, mass 1, whatever you like to call it. Now, the mass of the object is 24 kilograms. We know that it takes, now this is going to be the interesting part, it takes Fp, it takes 75 newtons to get it moving. Now, what's the forces that, what are the forces I have not drawn so far? What forces am I missing? Give me some of them. Ariel? Gravity for sure. What else? The normal force. And
The frictional.
frictional force. What do you think FFS means?
For friction, static friction.
Yeah, the force of friction due to the static force, okay? So FF means the force of friction, the S just means static. So why am I putting static? To indicate that this object is not really moving right now, okay? Anything less than 75, like 74.9, it's still not moving. As soon as this person gets to 75 newtons, it starts to budge. It just starts to move. So remember how we were talking earlier in the year with projectile motion? When you found the impact velocity, it was the instant before it hit the ground. Remember impact velocity, where an object is launched, flies through the air. You want the velocity of impact, which is the velocity the instant before it touches the ground. Because if you find the velocity after it hits the ground, it stops, right? It becomes zero. So we're finding the velocity instant before it hits the ground. Here, right here, we're looking at the instant before it starts to move. The instant before it begins to move. So it's still stationary. Okay, it's still stationary, but it does take 75 newtons just to get it to move. 74.9 is not enough. It takes 75 newtons. And that's where we talked the other day about static friction and how it can vary. Now let me make sure I go over this again, because this is a test question that everybody always seems to either misconstrue or misunderstand. If I push on this garbage can with a newton of force and it doesn't move, it means friction is pushing back with a newton. If I push with 2 newtons and it doesn't move, friction is pushing back with 2 newtons now. As I increment my force and I increase my force, friction also increases until what happens? Until it moves. And then I've overcome friction. So friction is a variable quantity. Let's write that down. Static friction specifically can change. It's a variable quantity. It's a parameter, you might call it. Okay, so static friction is a function of the amount of force you apply. It's a variable quantity. It's a parameter that can change. You could use any of these words. Variable quantity, parameter that can change. You could say that the static friction is a function of the amount of force you apply. So static friction depends on how much force you're applying. Now, if it takes 75 newtons just to get it to move, okay, it means that we can't use 74.9 as our force that we apply. It's got to be at least 75 just to get it going. Now, remember, and jot this down. These are like little notes I keep telling you guys that you should write down that I say I don't write them. These are things you should write down. You should write a little asterisk that says, we're analyzing this problem the instant before it begins to move. We are analyzing this problem the instant before it begins to move. And that's always true when you're using static friction. Whenever the problem involves static friction, you're looking at the instant before it begins to move. So if you recall from last class and the class before, there's only one equation that governs all of this chapter. What is it, Nick? F equals ma. Now, here's where it's going to get a little bit tricky. Just a little bit. Just a little bit. We have the x and the y. What forces are acting in the x direction in the diagram above? All right, help me move. FP and FFS. Absolutely. Those are horizontal. Which ones are vertical? Gravity and the normal force. So we are going to, again, look at 2 directions like we did with projectiles. It's not as difficult as projectiles, but it's still going to involve x and y. So let's go ahead and make a little table like we've done in the past. We've got the x direction and we've got the y direction. Now, in the x direction, and again, in both directions, we have this formula. The sum of the forces equals ma. The sum of the forces equals ma. What is the difference in the 2 sides? My subscripts, that's all. So on the left, I'm looking at x. So I need to literally, for those of you that struggled last chapter with knowing how to just when you start a problem, a lot of you struggle with that. Physically knowing what was going on. These problems are all based on your diagram. So if you're struggling with these problems, you need to practice making diagrams, actually. Once you have the diagram, the rest of it is actually really easy. What in the diagram, as Ariel told us, acts horizontally? What acts negatively in the horizontal? What acts negatively in the horizontal? Sophia?
FS.
Yeah, so we go ahead and start with that. I could have started with FP. I don't care. It doesn't matter which way you start it as long as you apply the correct sign. Tom, which way does FP act? To the right or to the left?
To the right.
So we put a positive there. Okay, so that's all we have to do for all of these. Literally list the forces. That's what the sum of the forces means. It means look at your free body diagram and literally write out the force names. Give them negative signs if they're acting left. Give them positive signs if they're acting to the right. Now, we're looking at this the instant before it begins to move. The instant before it begins to move. So what else can I say? If it's not moving, the instant before it begins to move. Ariel? Zero acceleration. Okay, zero acceleration. Extremely important. Now, almost every single time, I want to say every time, almost every time, your y direction will have zero acceleration, unless it's floating or being lifted off the table. Okay? Unless an object is being lifted off the table, if it's on a surface like it is here, it's on a surface. It's not moving vertically. Its only desire is to move horizontally. You will, if it's not moving vertically, always set a y equal to 0. So the right side, you're also going to have 0 here. But the question is now, what are the forces? What force, in this case, let's start with the positive. Last time I started with the negative. Doesn't matter. What forces are positive in the y direction? Or what force or forces are positive in the y direction? Liam, help us out here. In the y direction, which force is positive here? So we're looking here, right? Which of these two forces, Fn or Fg, which is acting up? So that's the positive. And then what's acting down, Liam? So all we do is write that. Okay, it's the same thing as the x direction. In the x direction, we have friction acting to the left, so it was negative. And in the y direction, we have gravity acting down. It's negative. See how I started with the negative in the x, but in the y direction, I started with the positive? It does not matter. It does not matter. You can literally just list all your forces in that direction and then put the signs afterward. Now, what's our goal? What are we trying to figure out? What are we trying to figure out? What does the problem actually ask us to find here? What does it say to find?
The static friction.
Not the static friction. Be careful.
The coefficient.
The coefficient of static friction, which is mu. That little mu symbol we're going to try to determine. Mu is the goal of your lab, really. Okay, so once we do another problem, we're going to go back to your lab and show you how mu comes up. So we're going to try to figure out something that's embedded inside of friction. Go to your last slide. What was the formula for friction? Yeah, so this is FF right here. So what I'm going to do is, I'm going to replace this with mu Fn. What is the S for again? Static mu. Mu always is going to have an S or a K, either one. The general formula I gave you on the previous slide encompasses just friction in general. But if it's static versus kinetic friction, there are differences here. Okay, good. So far, good. Plus Fp equals 0. So it looks like in the x direction we might have everything, but the problem is we don't have Fn. Right? We have Fp. What's Fp? 75 newtons. Mu is what we're looking for, but we don't have Fn. So where might we see Fn? Where do people see Fn? Look around the page, somewhere else. Where else do you see Fn? Aiden, help us out. Where do you see Fn?
Where Fn minus Fg.
Yeah, it's over here. So what is Fn in this chapter? What do we call it? We did it like this with projectile motion. It's like time, remember?
It's a shared variable.
Linking or shared variable. Very good. Good memory. Remember how time worked in both the x and y direction? So if we could get Fn here, which we can, how do we get rid of Fg? We add it. So move Fg over.
Oh, it's the same thing.
It's the same concept. That's why I think the year gets easier for students as tests go on. Because we take the concept from linking variables in two directions and we apply it here now. And it's a little bit easier than projectile motion was. There's not many formulas. There's one formula. F equals ma. That's it. Okay, these other formulas like mu Fn goes in for friction, that's given to you on your formula sheet. What should Fg be replaced by? Fg always equals what?
Negative 9.81.
No, be careful. Fg equals, look at your formula sheet if you have to.
Mass times gravity.
Good. Fg is always equal to mg. Remember, the weight of an object, Fg, remember Fg is the weight, is equal to its mass times 9.81. On Earth, obviously, on Earth. So as a result, what we can do is we can move the mg over. Let's move mg over by adding it. And we get this. Well, the normal force is equal to the weight. Why is that happening here? Let's take a look back to the pencil case problem. Here's the pencil case, right? Pencil case is at rest. It's sitting still. Gravity's pushing down. Normal force is pushing up. So those are in balance, aren't they? They're in equilibrium. That's why this is true right here. Even if I do this, watch. I'm pulling, right? I can't overcome friction, and then I hit 75 newtons. And it starts to move. Well, even if I'm pulling, and even if it does move, it's still moving which way? Horizontally. So in the vertical direction, this is still true. If no force is applied in the vertical direction, then this is always true. Fn equals mg. Okay, this is when there's no force applied either, again, at an angle, because at an angle is also vertical. If no force is applied at an angle or in the vertical direction, no external force, then this will always occur. Fn will equal mg. Okay, it's when we have things at an angle where we're going to see later in the chapter, a little more confusing of a question, that we have to incorporate that. Okay, but for now, this is true. So we take this quantity, mg, and we think back to math, and we think to Algebra 1, we think the substitution method. Remember when you use substitution method? Elimination and substitution? You substitute mg in for Fn over here. So take this quantity, mg, plug it in right there for Fn.
Could you solve for it?
You can. Okay, now what we'll notice is m is given, g is given, Fp is given. The only unknown now in this equation is mu. That's the only thing we're missing right now. So I'm going to subtract Fp. And you could plug in numbers if you'd like. I don't mind, again. I'm going to subtract Fp first. Then watch what I'm going to do. I'm going to divide by negative mg to get mu by itself. Because if I just divide by mg, I get negative mu. I don't want negative mu, I want mu. Yeah, mu and m are different, so make sure you are able to notice that. And the mu that I write, take a look at my mu. It's got like a little angle it comes up with. Okay, mu with the subscript of an s. So I take this equation, I move the Fp over, and I've got negative Fp. I want to get rid of mg and the negative, so I divide by mg negative. These cancel out, leaving me mu. I've got mus, negative mg into Fp. There's negatives cancel, making the answer Fp over mg. Okay? Fp over mg. What do we get as an answer for this? What was the mass? What was it? M is mass, G is gravitational constant, 9.81. What is the mass? What was the mass? 24? Remember, this is one of the few times that we leave kilograms as our units. So 24 kilograms, stay that way. You don't have to convert that to grams. You leave kilograms always. That's our fundamental unit for mass. Make sure you do the product first and then divide it into 75, or just simply put parentheses around your denominator when you put it in your calculator. Nick. Can others verify that? No? Be careful. It means you didn't put parentheses.
For the mass, sorry.
Ah, yes, the mass. Or the weight, then divide it into 75.
Yes.
Okay?
Or 3.9. And 3. .319.
If you ran it properly, it'd be 319. On your lab, you'll notice that I asked you to keep to the 100th for your data and then for the 1000th because of the fact that these are very, very small incremental changes. Mu is traditionally between 0 and 1. Okay? And its value cannot be negative. It wouldn't make sense. Let's jot these notes down, right? Mu can't be negative. Mu is a coefficient. It's a parameter. It's like density. You can't have a negative density. Density is a material property. Mu between Christina's pencil case and Isabella's notebook is different than the mu between the pencil case and the table. So mu is a function of how many surfaces?
2.
2 surfaces. Let's write that down also. Okay? So if I can't say the mu value of glass or the mu value of ice. It needs to be, find the mu value of glass on ice or metal sliding over ice, like a hockey puck or whatever. Is a hockey puck rubber technically?
Yeah.
So it's some sort of hard rubber on ice. There's a certain mu value. It's very low, so it slides easily. Now, if I look at the mu value between my rubber, I told you yesterday, remember the rubber in your soles and the concrete outside, that's a very high mu value. If you were walking and you had to stop suddenly, you could stop easily. On this floor, if I'm running and I try to stop, I kind of slide for a little. Scared? But if I'm outside and I did that, I would stop instantly. Because mu is a little bit higher between rubber and concrete. The mu between rubber and whatever this floor is a little bit lower. Okay? So mu is a function of 2 surfaces. 2 surfaces. The higher the mu, the more the friction. The lower the mu, the less the friction. I think I want to do one more. Let me just check before we get to the lab example I want to make sure we're clear with. Let me see. Yes. Yeah. Actually, I'm going to jump right to the lab example because this is a perfect time for that. I didn't realize. It's a perfect time for it before we get to the angular stuff. So let's go to lab 5. Take out that lab, please, from yesterday. And we're going to look at the first page on the bottom there. Okay, let's open up, look at the first page on the bottom. Okay. Now, recall from yesterday what you had to do. You had to determine the force needed to get something to move at a constant velocity. Let's go back and think about that for a second. You had to determine how much force was necessary to calculate, or to, oh, you're going to calculate, but to get the object moving at a constant rate. At a constant rate. So, if we draw a free-body diagram of yesterday, here's what we have. Here's what we have from yesterday. We've got you pulling on it horizontally. What's pushing against it? Against motion is friction. Now, we were trying to do this yesterday and get it to be moving at a constant rate. So if it's moving, come on guys, focus. If it's moving, we are no longer looking at static friction. That's when it was stationary. Your goal yesterday was to determine the mu value while it's moving. What kind of mu is that again? Anybody remember the term? Not static, but what? Kinetic. So we are trying to find FFK, really, so we could find mu K, the kinetic coefficient. Next. Acting down is gravity again, and acting up is the normal force. So everybody pause for a second and just analyze this diagram. Look at it. It should look a whole darn familiar. This should look really familiar. It's the same diagram as the last problem we just did. And it might not be obvious at first, because in the last diagram, I put FP on the left side, didn't I? And I put friction on the right side. But the arrow for FP is still pointing to the right, just like it was in the last example. The arrow for FF is still pointing to the left, just like I did in the last example. So those first beginnings of the equation are pretty much the same thing. The only difference we have to consider is that it's moving. If it's moving with acceleration, we can't set it equal to 0 anymore, Because remember, sum of the forces equals ma. If it's moving with acceleration, we can't put 0 in for acceleration. But what do you know about the lab specifically?
I have a question about the diagram. Why did you switch them?
Why did I switch to?
Like FP, like,
Does it matter whether I pull an object from over here, Anthony, or if I push it from that side this way? Isn't it the same effect? So it doesn't matter? So I'm just doing it just to change it up for you so you can see that it's the same thing. Again, ready? Last problem, take a look up. I was pushing, wasn't I? And now this problem, what am I doing? I'm pulling. But both problems, I'm still pulling to the right. So friction is still acting to the left. So it doesn't matter where I put it on the diagram, it matters what direction the arrow is facing. Okay? So FFK is really the same thing as FFS in the last problem. Same thing, both acting left. FP is still acting to the right. So let's go back to the question I was asking. The only difference here in these equations is that there could be acceleration now because it is moving. But what about the lab did I specify? What did I tell you? You wanted to calculate the force that you needed to pull it to get it to move at what? At constant velocity. That's the key. In the lab yesterday we said we wanted to move at constant velocity. Constant velocity tells us that there is no acceleration. So it turns out that the solution to our lab from you is the same as the problem we just did. Let's prove it. It'll be the exact same work, literally the exact same work. So in the x direction, we've got negative FFK instead of FFS plus FP equals mass times acceleration. In the y direction, we've got negative FG plus Fn equals m times acceleration in the y direction. So it's the same exact equation we just had a moment ago. And for a moment, it seems like maybe it's not. You know what? Maybe there's some acceleration. But I specifically told you in the lab to get it to move at a constant rate or a constant velocity. When you have constant velocity, you have no acceleration. When you have constant velocity, you have no acceleration. So this turns out to be the same thing as the last problem. It's literally going to be the same solution. So if you want to jump ahead, you can on your own. I'm going to do it though. So the same as last time, we're going to replace friction force with mu Fn always. That goes here. But now instead of mu S, it's mu K. Because it's in motion, it's kinetic. Fp is still Fp. That's what you figured out in your lab. Remember you had to find 5 Fps and then average them? That's what you're going to utilize there. Mg goes in for Fg always. And again, it's the same as the last problem. It's literally the same thing. The solution we're going to get is going to be the same. Except instead of mu S, it's mu K. That's the only difference in this problem. Again, because there's no acceleration. We're going to see some problems in the rest of this chapter. We're going to do these where there is acceleration involved. And then you cannot just put a 0 in over here. You have to put the mass times whatever the acceleration is and utilize that in the problem itself. But for these problems, we don't have to worry a thing about that. So I'm going to do this again. I'm going to get Fn by itself on the right-hand side. I'm going to substitute. I'm going to substitute this mg right here in for Fn right there, giving me the same exact equation as the last question. Solving from UK, I'm going to get, again, the same answer as the last one. It's going to be negative FP over negative mg. So I'm dropping both negatives for the sake of that. It's the same answer we just got. That's the beauty of physics. Think about that. It really is amazing. Completely different scenarios. I'm trying to overcome static friction just to get this moving, and the same equation governs me moving this at constant velocity. This is apparently the same thing as this. It doesn't seem like it's the same, but mathematically it's the exact same thing. That's what modeling does for you in physics. That's why you make models. And models don't mean not necessarily physical models. Models. A modeling of the equation. So this is the coefficient of static friction between, remember, the felt and the table. Teflon and the table. The cork and the table. They're going to be different answers for all of those, right? So what you need to do is take a look and see what your average FP was for a certain scenario. So let's take a look at, hypothetically, let's take a look at felt. Okay, it was called felt? Did I call it felt?
Yes.
All right. So let's look at felt with 2 weights. Remember, there was felt with 2 weights and there was felt with 4 weights. Then there was Teflon with 2 weights and Teflon with 4, etc., etc. When felt had 2 weights, what was the mass? Look at your table, please. It's already listed. Felt with 2 weights. What was it, Caroline?
0.2836 kilograms.
And it's really important that you keep your decimals right now because we're doing a lot of calculations. And a lot of stuff with mu and friction is very small numbers. So don't round to the nearest 10 because that would look like 0.3, right? It's a big difference. All of the masses would become 0.3 if you rounded to the nearest 10s for all 4 of them. But there's actually a difference between the felt and the cork and the Teflon's mass. So those were all different. That's the mass. Okay, gravity is gravity. What was your FP, Caroline, your group? For felt with 2 weights, what was your average of those 5 numbers? Okay, any group average it? It's okay. Any group average it yet?
No.
All right, so on your own, do it right now. Average your 5 numbers for felt with 2 weights. Go to your numbers from your lab. Felt with 2 weights, or do it for cork, whatever one you have done so far. If you haven't done felt yet, do it for cork. Average your 5 numbers for FP to give yourself some value for FP bar. Remember FP bar, the bar just means average. Okay, just means average. Give me a sec, I want others to have a moment to do it. And guys, remember, your group's not going to be the same as other groups, right? It's not going to be the same answer. It's fine. It might be different by a little bit. It's all because of the way you actually perform the experiment. Ariel, what was your groups?
To the nearest 10?
Give me the nearest 100th if you could.
Okay, 1.05.
So that's the nearest 1,000th. I'll take that. That works. Right? 10th is 1 digit. So 1.052. That works. What were the other groups? I'm curious. Give me your group, Nick. What was it?
1.11.
1.11. Javon? 1.37. Other groups have their numbers yet? I'm just curious where the ballparks were of the numbers we got. Okay. So, here's what we're going to do. We're going to take 1.052, put it in the numerator. That's FP. That goes right here. The mass is the same. Doesn't matter what group you're in. Same objects. So we take the mass, 0.2836 times 9.81. Remember, the denominator needs its own parentheses if you're going to do this all in one step in your calculator. So that's how you would find UK for felt with 2 weights. For felt with 2 weights. Ariel, could you tell me what your number turned out to be for this? Come on, Vinci, quick. Use those texting hands we all know you have. You guys are so fast at texting.
It's not words,
Who texts anymore?
Who texts anymore? Talk to text? Oh, telepathy. That's even better. Kill me. What do you got?
36.5.
36?
Yeah, that's not right.
Can't be right. Come on. Parentheses surround your denominator, please. You did 1.052 divided by 0.2328, and then you multiply that by 9.81 accidentally. You need parentheses around your denominator. 0.2836. It's this number right here.
Oh, okay.
Okay, 0.3781.
Okay, that's what her group got. Now, because it took more force for Siobhan's group, I assume your answer is bigger than that, Siobhan.
Yeah.
What did you get?
Nice.
I'm using parentheses, so we can. Real quick.
Damn.
45
Another group. You're making a mistake. Come on. You are. Any other groups get an answer?
Close parentheses.
Come on, people. This is like 9th grade typing in your calculator right now. Please. Chris, thank you.
0.271.
Okay, 0.27 for his group. Now, Chris, what was your FP average?
0.7794.
Yeah, so his FP was much less than this, wasn't it? Was that felt, or did you do cork for that? Yeah. So he did it for cork. So his cork value came out to be less than 0.378, which means there's less friction from the cork than there is from the felt. The felt has more friction in it. What are my units from you? What are my units from you? Figure it out. Don't just take a guess. Think about it. Look at what mu is equal to. Look at the equation from mu and think about what the units of mu should be. Go through your dimensions. Come on. You should be able to do this by now after this year. If you can, it's really, I feel like a failure right now. Come on. If you want to figure out what the units of mu should be, look at the actual equation. What are the units of force right here? What are these units? Okay, so we have a Newton, right? That's the top unit. What are the units of mass times gravity?
Kilograms and,
No.
oh no, wait.
Yeah, kilograms times what? Which is really a, what is it? It's a Newton. I'm hearing very little confidence in your voices though. So this is really kilogram times meter per second squared. That's really a Newton. So it's a Newton over a Newton. So what are the units? A Newton over a Newton does what? So what are the units? Nothing. There's unitless. There's no units. Because a Newton over a Newton cancels, right? If I have a certain amount of Newtons divided by another certain amount of Newtons, I look at my units. Newtons over Newtons cancel. So there are no units to mu, ever. There are never going to be units for mu. It's always going to be Newtons divided by Newtons. Always. You don't like it? Yeah, you don't like it. You want to know why there's no units? Because it's a rating. It's an experimentally determined rating. It's a value. That's literally what you guys did yesterday. Was one of the first ways scientists discovered mu values or learned how to derive them. They applied a constant force for a given amount of time, applying a force over a certain distance. They calculated the amount of force it took. They knew the mass of the object. They then derived the mu value. It has no units to it whatsoever. Okay, it has no units. What time does this bell ring?
25.
Okay, so we have like 3 minutes? Good. Okay, does that make sense? No units? Again, Newtons over Newtons. They cancel, so there cannot be units if they cancel. Let's take a look at another example real quick. I'm going to make up this example, so just add a little slide, please. You could write this down in words if you want. Let's say an object is pulled. An object is pulled by a force of, we'll do that next, a force of 55 newtons. An object is pulled with a force of 55 newtons. Its acceleration is 1.2 meters per second squared. Okay, its acceleration is 1.2 meters per second squared. Determine the value of mu. Determine the coefficient of kinetic, because it's moving, kinetic friction.
And we still use X and Y, right?
Still going to use X and Y, but now we have acceleration. Now we have acceleration. So we can't use the exact same answer as the last problem. Let's see how that answer is going to change. So I'm going to jump to my X and Y directions now. In the X direction, I've got negative friction. It's pushing back. I've got positive FP. It's pushing forward. And that equals MAX. Again, remember, sum of the forces, that's what this is, equals MA. A is not going to drop off this time in the X direction because we're told that it's got acceleration. I should say it's got horizontal acceleration, really. It's AX. In the Y direction, I've got gravity pulling down, the force due to gravity, the normal force pushing up. Now, this object is not floating off the table. I'm just pulling it to the right with some acceleration. So there's no vertical acceleration. So here, MAY becomes 0. But remember, MAX is not 0. So let's go through this now. We need the mass of the object also, by the way. Let's say the object's mass is 8 kilos. Okay? 8 kilograms of the mass. So if we want to go ahead and solve for mu, we could start by replacing this with mu k Fn. You can always do that. Okay, if you're trying to find mu, if you're just trying to find the force of friction, you don't have to replace this. You can just solve. We'll pick this up next time, okay? Try and see if you can do this at home if you want to. Now, please, guys, please consider, don't forget, tomorrow your projects are due. Okay, if you don't have them done, make sure you get them done over the weekend. Okay, don't assume you have time tomorrow during the day to come in here and work on a project. It's not going to happen during the day tomorrow. Because they're due tomorrow. It's not like you're coming in during third or fourth period to do it. Okay, if you want to come in before school and someone's here, then that's fine, but I'm not going to be here in the morning. It's a very long section. Yeah, 3-3 was just as long. Remember 3-3? We did like, well, not just as long as well. What do you notice? What looks similar, please? Somebody point it out, Sean.
Projectile motion rules.
Yeah, it's the cosine sine vector rules. Vector rules, right? When you want the x component of a vector, you look at the cosine. When you want the y component, you look at the sine. So let's look at an example of what I'm pointing to, right? Here. Let's say that an object is on the ground right here. A sled. Okay, you're pulling your brother or sister, the younger sibling or cousin or whomever in a sled in the snow. And when you pull on a sled, usually the sled is actually much slimmer than this, right? It's like along the ground. Let me do it a little bit better, just so I can make sure you see what I'm saying. That's the sled usually, right? And then you pull at like some sort of an angle on a rope. So this is the kind of problem that we're interested in now. So we've already looked at the vertical and the horizontal separately in the last example. We did that yesterday. We incorporated friction. Friction and the pull were x, and the y was normal force and gravity, or weight. Now, our pull is going to be at an angle. So what we need to do is, just like we did with that flashlight, extra credit, some of you did, shine a flashlight from above, well that's the FPX. And shine a flashlight from the left, that's FPY. So if you recall, what we're doing is we're breaking this into components. These are the vector components. And please make sense of this. In your lab, your goal was to pull on that cart, or that, whatever that thing is called, the little bin, the tray, horizontally. If you pulled at an angle, the cart would lift up off the ground. That's what happens here. Think about last time you pulled someone on the sled. If you pull hard enough, doesn't it kind of lift off the ground a little bit, the sled? It's because you're kind of pulling up, FPY. But you're also pulling over, horizontally, FPX. So again, if you pull at an angle, we need to start by resolving that force into its components. And then when we look at our math, all we need to do is use the components. We don't need to use the actual force itself. So literally, on your free body diagram, if you drew FPX and FPY the way I showed you here, then you could technically just cross this off now. It's like it doesn't exist. Okay? When you do your equations of motion, sum of the forces in the x equals ma, sum of the forces in the y equals ma, you can use FPX for the x direction and FPY for the y direction.
I'm solving for hypotenuse again.
No need to. No need to in this case. Okay, because we're breaking up the hypotenuse into its components, actually. That's what we're doing. We're given the hypotenuse in a lot of these problems, and we need to know what the x and the y are. Remember how I was giving you velocity always, and you had to find VIY and VIX? Same thing. Okay, we're not coming up with the hypotenuse, though. We don't need to. We could at some point. You should be able to do it, but not in this problem. Okay? Can I get someone to demonstrate this? What would this look like? Sam and one other party, 2 people. Sam and Francis, come on up. Sam and Francis, all right. So, Sam, you go at the end of that desk. Francis, you come over here at the end of this. So, it says 2 students are sliding on a sofa at a constant speed across a wooden floor. So, Francis, you be the first student. One student pulls with a force of 225 newtons at an angle of 13 degrees above the horizontal. What would that look like? If you were pulling on the sofa at an angle of 13 degrees above the horizontal.
Upward and that.
Yeah, so show with your arms. Extend your arms so we can see the angle. So look, hold on to the sofa. So the angle, back up a tiny bit, okay? The angle is right here. See my hand here? My hand is the horizontal. The desk is the horizontal. Extend the horizontal. The angle is right there. That's the 13-degree angle above the horizontal. Now, Sam, on the other hand, though, is going to push. Right? She's pushing on the desk this way. You don't have to push, but show it. And it's going to be 23 degrees below the horizontal. So take a step back. Okay, extend your arms like you're going to push. Okay, so look, this for her, the angle is up here. Look what it says. It says 23 degrees below the horizontal. So my arm is the horizontal. Her arm is the force. This is 23 degrees. Do you see the difference in these 2 problems? This person is pulling 13 degrees above the horizontal. Hers is below. So technically speaking, Francis is pulling this way, and she's kind of pulling up. Whereas Sam is also pushing this way, but she's kind of pushing not up, but down. So her force in the y direction is going to be down. Her force in the y direction is up. She's pulling up. Sam is pushing like that. So the y component of Francis is up. The y component of Sam's is down. Both of their x components are to the right way. They're both trying to push it this way eventually. Okay, thanks, David. Good. Okay, so we're going to draw that diagram. So it's easier to understand it when you visualize a little bit better than just reading the problem. Carolyn.
Is it always when you're pushing that the angle is from?
No, it just depends on the problem. Context of the problem. So I'm going to first draw Francis pulling with the force. I'm going to call that FP1. I'm going to call that theta 1. FP1 is 225 newtons. And the angle that she's pulling at is 13 degrees. Then I've got Sam on the other side pushing, but she's kind of pushing down on this box at 23 degrees below the horizontal. She's pushing with a force of 250 newtons at an angle now of 23 degrees below the horizontal. So we've got this scenario that's happening, and we have to think about the fact that they're both pushing or pulling at angles. So what we can do is break these into components, okay? Now, there's other stuff happening. We know the mass is 225. Okay, 225 kilograms. We have the forces labeled. We have the angles labeled. What other forces act on this object? What other forces do we have acting on this object? Caroline, give me one.
Gravity.
All right, so I'm going to redraw it, by the way. I'm going to leave this. I'm going to redraw another diagram because I'm going to break the components up in a minute. Gravity.
Friction.
Which way?
To
And it says that they're moving at a constant velocity. So it's moving. So is it kinetic or static? Kinetic. Kinetic is motion. Okay, kinetic. FFK. FFK.
Will it go force even though it's kind of inclined?
We'll have to figure that out, actually. That's a really good question you ask. Because if Francis pulls hard enough, and it might lift it off the ground, and then it will be no normal force. But Sam was pushing down also, right? So we have to consider that. So there may or may not. So for now, let's put it though. Because there's a good chance that unless they're lifting it off the ground, like unless the two of them pick it up and move it, right, there's probably going to be a normal force. So let's try to figure out what that would be. Now, my FP2 and my FP1, watch what I'm going to do. Ready? So Francis was pulling to the right and kind of pulling upward. You see what I'm doing on the diagram? Look at what I've done. I've taken Francis' original pull, which was up and to the right, and I've drawn a force up and a force to the right. And I'm going to label them. FP1Y, FP1X. And again, it looks like a ton of subscripts, I apologize, but it is good to have the correct nomenclature. Okay? The force of her pull, the first person, to the right. The force of pull on the first person, upward, in the Y. So I've literally broken her forces into two components. How will Sam's forces be different than Francis's were? Nick.
The arrows will be pointing into the thing.
So tell me, you have two arrows, so tell me about each of them.
Arrow will go on the top right, the 8 going into the corner.
All right, got it.
And there will be an arrow going down.
Yeah, take a look. That's what's important. Notice, Sam was pushing this object to the right, but she was also pushing down on the object. So this is down and this is to the right. So these are different. Okay, those are different things. And this is FP2Y and FP2X. So again, just to make sure we understand this, the force of push from the second person in the Y direction, it's down. The force of push of the second person in the X direction, it's over. Well, when I do these mathematically, I'm just going to take my FP2, right, times cosine theta to give me this. I'm going to take FP2 times sine of theta to give me this. I'm going to make that a negative because it's down. Then over here with Francis's work, I'm going to take FP1 times the cosine of theta 1 to give me FP1x. And then FP1 times the sine of theta 1 to give me FP1y. So how many forces are in this diagram? How many are in the x direction? Take a look. How many in the x? Altogether, how many forces? 3. 1, 2, 3. How many in the y? 4. 1, 2, 3, 4. This is the same problem as yesterday from this point on. Some of the forces in the x, some of the forces in the y. Literally list your forces. It's a constant velocity problem, so acceleration is 0. So this is an easy problem to do. All it takes is actually coming up with a diagram. This diagram that we just drew is the most important part. Okay, that diagram you're seeing now. That's what's important. After this, the equations are so easy. It's the same one every time. Sum of the forces in the x equals MAX. Sum of the forces in the y equals MAY. That's a y. MAY. These are both 0, so they both drop off because it's not moving vertically or it's not moving horizontally with acceleration. It's moving with a constant velocity. Now, I then have to go ahead and list my forces for each direction. What forces are acting horizontally with the correct labels, please? Positives or negatives correctly, but which ones are the horizontal arrows here? Just look at your diagram. Look at the arrows and give me positives and negatives. Good. And that's which way? To the left, so what am I to write? Good. What else? Good, and what else? Very good. Okay, there's my 3 things for the x direction. Again, all you're doing is listing the variables. That's it. You're listing the forces. You're applying negative or positive based on your diagram. In the diagram, the only one to the left is FFK. So I put that to the left. Ariel, in the y direction, please. In the y direction. Okay, well done. Very good. Do we see what Ariel is getting at there? Why are there 2 negatives here? Why isn't there 1 negative? Why are there 2 negatives here? Gravity's down, what else is down?
Sam's
Sam's push. She was pushing down at an angle, so her pushes to the right are down also. So FP2Y, the second person, pushed down, so that's a negative. That's it. These are our equations of motion. Now it's a matter of can you solve? You need to know what to substitute in the right spots. I'm going to start doing that. Nick?
Would it have been better if Sam just pushed in the front instead of pushing down?
Sure, like theoretically, if the other person had been able to squat and only push horizontally, it'd all be in the X. You could do that, sure. Or you could be on the front pulling.
So would there be less kinetic? Would it go faster?
Guys, these are really good questions, and these are things that ask on the test.
Or would
So
it
listen.
be easier to push it if she's pushing?
So because she's pushing down, it makes more sense to want to pull them, yes. But had she got a level to the ground or even below and pushed, it would have helped a little bit. But pushing down just puts down the ground. When you push down on the ground, it increases normal force. Increased normal force increases friction. So if you're moving furniture, you're better off pulling than pushing, for sure. Because when you push down, think about it. When I'm pushing down, I'm pushing against the ground, aren't I, kind of? So the ground pushes up more, which increases the amount of friction.
But don't you have
Right.
leverage when you push rather than pull?
Depends. I mean, if you have a rope and you're doing this, you're just backtracking, I can do a lot better this way than I can do this way. You think because you're pushing and you're like that, right? Same thing. Get your body in the same position and you pull backward. Okay, but at that point, you're not increasing the normal force by pulling up, and therefore the friction doesn't go up. By pushing down, you're increasing normal force in the end, right? Look, normal force, when you solve for normal force, what's going to happen? Is this going to add over? So it's going to take the answer for normal force, this is going to add on to normal force. And if you have more normal force, you have more friction. So pushing down an object actually increases the friction, so it's not ideal. Now, let's get back to the problem. Look at the x direction, please. In the x direction, friction is mu Fn always. So I replace this right here. I'm going to zoom out a little bit because it's going to be tough to see this in a minute. In the x direction, the friction is negative mu k Fn. That goes in for friction. Plus Fp1x is really Fp1 cosine theta 1. Remember, this is always Fp1, and if I want the x component, I multiply by cosine of its angle. And its angle is angle 1. Plus Fp2x. Well, that's Fp2 times the cosine of its angle, theta 2. That's the x direction. I'm going to run out of room, that's why I'm doing it like this now, okay? Look at the x direction. Please make sense of it. Go back up to the x and look. Fp1x is Fp1 cosine theta 1. Fp2x, Fp2 cosine theta 2. You're going to use the angles and all the stuff that you listed in the beginning as your givens to be plugged in. But again, what don't we know in this equation? There's one variable we don't know. Well, there's two. We're trying to find mu. That's our goal. It says find the coefficient of kinetic friction. That's what our goal is. We're trying to figure this out. What don't we know, Siobhan? Normal force. Fp1, that was the force applied by Frances. The theta is there 13 degrees, theta 1. Sam was Fp2, and her angle was 23 degrees. That's going to go here. But we don't know Fn. Where do we get Fn in these problems?
Fn equals Fg.
No, be careful. That's only if there's, remember, no vertical forces. Look at your y direction. Look at the y direction. Make sense of it, Nick. Yeah, you got to solve for it in the y direction. In the last problem yesterday, we said Fn equals mg, and I specifically said to you, only in the instance where it's only pulled horizontally is that true. But now there's other vertical forces. Frances was pulling up. Sam was pushing down. So there was more vertical stuff going on. So in the y direction now, Fn is a little more complicated. But all we have to do is solve for it in the y direction. I'm going to rewrite the y. I'm going to leave space in the x. Leave a little space here. In the y direction, I'm going to rewrite my equation. This Fg, the weight of an object is really mg. So we start by putting mg there. Fp2y. It's a minus, so it's going to be Fp2. And to get the y component, you do the sine of its angle. Fn is just Fn. And FP1y, which is right over here, is FP1 times the sine of its angle. So the x direction, the formula looks complicated because you have cosine and sine. Please don't let it confuse you. It's the same thing we did with velocity. In the y direction, if you want the y component, we use sine in both of those. This was negative because Sam was pushing down. The weight is negative because it's pulling down. Francis is pulling up, so this is positive. The normal force pushes up, so it is positive. Our goal in the y direction is to find out what Fn is. So move everything over except for Fn. Add or subtract over accordingly. Oh my gosh, these are all separate, really? The program, every time I move it, if I move the screen or use a different function like this, see I'm using different functions, it automatically restarts the image as a new image. It's so annoying, it's unreal. I don't know why, but I like the recording program, it's really great. But that part sucks. So, yeah, I've written to them. They haven't done anything to fix it. You can write to app developers and then sometimes fix it. Anyway, solving for Fn over here, literally move everything over by just switching the signs. So, positive FP1 sine theta 1 can move over as a negative FP1 sine theta 1. So subtract it over. The ones that are negative, these two, add mg to the right side. Add this to the right side. Subtract this to the right side. So literally just switch the signs. Add mg, add fp2 sine theta 2, and then subtract fp1 sine theta 1. Again, to get Fn by itself, you have 1, 2, 3 terms. Remember, Fp1 sine theta 1 is a term itself. You have 3 other terms, so add or subtract them respectively to the right-hand side. That's Fn.
Would gravity be negative 9.8?
No, remember, with forces, G is always just 9.81. Remember, Nick, take a look here, ready? This has already taken into account the fact that gravity is negative, right? Remember, it's a negative force? So it's already taken that into account. We move it over, so it looks like it's positive, but it's only because we moved it over in our mathematical calculation. But this is going to be the mass times positive 9.81. Okay? Next, in the x direction, we need to solve for mu. Where's mu? Mu's right here. See it? So we need to subtract this over, and then divide by Fn. Everybody following what I'm saying? Take a look up, please. Don't just look down. Look up. Subtract this over, and then divide by Fn because it's multiplying. We'll divide by a negative Fn, really. So we've got okay, when I move those over, that's what I get. So I move the forces over first by subtracting them. Then I divide by negative Fn. What happens if every term is negative? Negative, negative, negative. They all become positives if they all are. Remember, if you're dividing by a negative, you could just switch the signs to the numerator, which makes them all positive. So it turns out that mu k is given by the formula fp1 cosine theta 1 plus, I'm going to make them all positive, fp2 cosine theta 2 divided by Fn. Okay, I boxed it in so you can see better. That's what mu k turns out to be in this problem. Fp1 cos theta 1 plus Fp2 cos theta 2 all over Fn. Fn is right here at the bottom, so what should you do, you think? What should you do with the Fn that's at the bottom if we have that representation here? Yeah, not multiply, but what are we doing really? Plugging it in. Don't use the word multiply. Plug in. Okay, so we have to plug it in, please. This is going to be a mess to move. Let me just zoom out, actually. I'm going to zoom out again.
Why don't you just solve for Fn first?
Now, that's one thing you could do, right? What Nick said is get the Fn's number. Now, Nick, there's a chance that you might not be given the mass, and something might need to cancel out. So you might have to plug the whole expression in. In this case, though, you were given the mass, right? You were given everything else, so you could come up with a number. That works. You can definitely do that. We're not going to do inclined planes this year just because we're going to run out of time, and because I introduced this project, we're kind of doing inclined planes, and I'll explain some of the math when we go over the project, we discuss the project the day of. But in inclined planes, it's actually vital that you don't plug in because you're never given mass. The mass is irrelevant in an inclined plane. It cancels out. Okay, you end up with mass everywhere and they all drop off. But in this case, yes, you could plug in. But I'm going to do this, plug that in right there, giving me a final answer from UK of FP1 cos theta 1. Again, I'm just recopying what's above. Plus FP2 cos theta 2 all over Fn, which is mg, plus FP2 sine theta 2 minus FP1 sine theta 1. All the denominator needs to be in parentheses, or do as Nick said, and solve for Fn first, and just plug in a number in the denominator. Okay, the math itself, honestly, is not difficult. It's a matter of being organized. For those of you that struggle with organization, this might be tough. You need to be organized. Okay, you solve in the y direction for Fn, plug it into the x direction for Fn, which is in our generic solution from UK, giving us our overall generic solution. Everything in here is known. FP1, that's Francis's force. Theta 1 is her angle. FP2 is Sam's force. Theta 2 is her angle. Well, we're going to use those same numbers in the denominator, but sine instead of cosine. Mass was given. The mass of the couch was 225 kilograms or 250 or something. G is 9.81. Literally plug in at this point. Okay, please literally plug in at this point. I'm going to plug in up here. All right. Oh, geez, here we go. FP1 was, let me just make sure I have the right diagram on mine, it's the same as yours, 225, right? Okay. Yeah, it's a lot of work, right? You see how much math is involved? Plus the other force, which was 250, times the cosine of 23. That was the angle that Sam pushed at. All over. M times G. Mass is 225. Times 9.81. Remember, it's positive 9.81. We already took into account the negative sign earlier. FP2 is 250 times the sine of angle 2, which is 23 degrees, minus FP1, which was 225, times the sine of 13 degrees, all in a bracket. Okay, that's your final answer right there, that whole thing. What do you get? Anybody actually get it? It's a lot, I know. Trust me, I know this. You never would think that one answer could be all that. Nick?
I got 0.2.
Give me like a few decimal spots. 0.199?
0.19927.
Yeah, nice. Now, notice, I didn't plug in any numbers earlier. I waited till the end. The reason? Sine and cosine plugging in earlier could cause a lot of errors in your answer. Remember we talked about cumulative error that time? If you round early, and then use a rounded answer in your next answer, and then round that, and use another rounded answer in the next answer, it's called a cumulative error. So if you plugged in these numbers really early and had decimals, like say 250 sine 23, what is that? What's
219.23.
Yeah, 219.23.
23.
If you just put like 219.2 in your rounding, it's going to cause this to probably be off by a little bit in the end. So that's why I leave everything the way it is and plug it in all in one line. You could do this all in one line in your calculator. Okay? All you would have to do is put parentheses around your whole numerator and your whole denominator each, please. Okay, do the whole numerator in parentheses and divide by the whole denominator. But every time you have an open, you need to have a close. So if you open, you need to have a close at the end. So literally type it the way you see it and it will work. A lot of work for one answer, right? Okay, do we see how that works with a free body diagram? Let's look at the next one now that's very similar to this. Okay, by the way, this is a very low mu value. Remember your lab? What did you get for Teflon in your lab? Can you look real quick? What was your mu value for Teflon? take a quick look if you guys have did yesterday. Some of you did corn and felt and forget to calculate them all while we were in class. Did anybody calculate Teflon's U value yesterday? The one on the bottom, I think.
That one?
Yeah, but the mu value is what I was looking for. What do you got? 0.204. Yeah, look. 0.199. This example is most likely Teflon on some sort of a plastic coating. Remember, mu is a function of how many surfaces? Two. Because they are interacting with one another. Does that make sense? We have about 5 or so minutes left only. I want to start the next one at least. It moves a box by attaching a rope to it and pulling with a force of 90 newtons at an angle 30 degrees above the horizontal. The box has a mass of 20 kilograms. And the coefficient of kinetic friction between the box and the sidewalk is 0.5. So we're not solving for mu anymore. That's fine. Doesn't matter. What are we solving for instead? The acceleration. Which way is it going to accelerate? It's going to accelerate right or left, so in the x. So we're trying to find ax. It's not 0. It didn't say constant velocity. It didn't say it was static friction. It says kinetic friction. So it's moving, and there must be acceleration. Maybe the acceleration is 0. Who knows? If it's 0, it means that you're in perfect equilibrium, and the force you're pulling with is balanced by friction, so you're moving at a constant rate. It could turn out to be 0. It doesn't, just so you know. It could, though. It easily could turn out to be 0, and then your part B might say, since accelerate, what could you tell me based on your acceleration? If you got 0, you could say, well, it's moving at a constant velocity. It's in a state of equilibrium. Okay? So in the x direction, in the y direction again. In the, I should draw my diagram, right? Now FP, what could I do? Instead of writing FP there, I could erase FP and draw in FPX and FPY. And I'm going to just cross this off now. Okay, I could replace it with its corresponding components. If it's at an angle up to the right, it's got up and to the right as its components. So now in the x direction, we've got FPX and FFK. In the y direction, we've got FG, Fn, and FPY. 3 forces in the y direction, 2 in the x direction. In the x direction, I've got negative FFK, positive FPX equals MAX. I didn't write sum of the forces equals MA. Honestly, if you don't, it's okay, as long as you know that you're plugging in the forces here. In the y direction, I've got FG pulling down, I've got Fn pushing up, and I've got FPY pushing up. And it's not, well, we don't know if it's moving vertically. I shouldn't say it's not. Well, it didn't say it in the problem, so we could assume it's not. Okay, so 0. Let's figure out our answer. As a result, we're trying to find AX. Plug in everything you know. FFK is mu Fn. FPX is FP cosine theta. And that equals MAX. In the y direction, FG is really mass times gravity. Fn is still Fn. FPY is FP sine theta. And we're going to do the same thing, again, linking variable. Solve for Fn here. You're going to get a positive mg by adding that over. Add that over. Subtract this over, giving you a minus Fp sine, God bless you, theta. This expression, mg minus Fp sine theta, is going to go in over here. As a result, I get this, negative mu k times that whole expression, mg minus Fp sine theta, that goes in for Fn. Remember, that's replacing this right here, plus Fp cosine theta equals m. Now, what do I want by itself? What are we trying to figure out in this problem? What's our goal? So just divide the whole thing by? No. M. to get rid of the m. So you take this entire equation, divide by m, divide by m. Okay, you're dividing both sides by m to get ax by itself, so that's where the m is here. You're replacing fn over here for fn, that goes right there. Negative mu k carries down, ft cosine theta is here. Plug it in, and you can figure out ax. I will show you the substitution real quick so you can see. It becomes negative, what's the numbers? Mu k was 0.5 times the mass, which was 20, times 9.81, minus Fp, which was 90, times the sine of 30 degrees. Now, recognize, please, this whole thing here, mg minus Fp sine theta, needs to be calculated or put in parentheses in itself. That answer gets multiplied by negative 0.5. Plus 90 cos 30. Projects, before you leave, projects, don't think I forgot. Okay? I need projects from everybody.